Okay, so I want to talk about this week's problems. There are 5 problems. And actually, the first one and the last one are a little bit different. But actually, maybe I'll talk about the last one and the first one and last one before I talk about the other 3. The other 3 have a little bit more of a theme. So let me just move that around. All right. Okay, so the first problem is hopefully a warm-up problem, but um, there's still perhaps some things to learn. So basically, again, I'm not going to read the problem, so you can go and read the problem to find out what this is about. But basically, you have a certain number written in one base, and then you need to convert it to a number in a second base. The only thing that is a little bit strange, I guess, is that these are not necessarily the standard digits 0 to 9, but it can be any of these letters as well as uppercase, lowercase letters, and 0 to 9. So for example here, um, let's look at this one. If this is the digits in the original base, you have 1, 2, 3, 4, 5, 6 different characters for the digits. So 0 is O, 1 is exclamation mark, 2 is C, D is 3, E is 4, question mark is 5. And you should be able to tell that this is actually base 6, okay, just from the length of this string. And then here, this is 1, 2, 3, 4, 5, 6. It's also base 6. So actually, in this case, there's actually no base um, conversion. It's just translation or substitution of the digits. Okay, but apart from the fact that the digits are not the usual ones, there's really nothing different from a normal conversion. So I guess what I want to talk about, I guess, is conversion, if you know how to do that or not. Okay, so the first one is, what is a string or any other base to decimal conversion? And then you have decimal to whatever other base, right? So how do you convert from base B to a decimal, and how do you convert from decimal back to base B? Now, the one thing that I want to say, and this is something that maybe a lot of people don't think about, is there is no such thing as decimal. Okay, so what do I mean by that? Base B already includes decimal if B is 10. And what I really, really want is to turn a base B representation into the integer value that you can use store inside the computer. So let's say integer variable. And by the way, the problem says that no numbers will be bigger than a billion. So normal 32-bit integers is good enough to store the value. When you actually store things inside a computer, it's a variable that holds the integer value. It doesn't actually store this into base 10. In fact, it stores stored as base 2. But it's convenient to think about base 10 and actually just convenient to think about the value. Okay, so that's a little bit of a, I don't know, picky distinction of what many people say, convert from base 2 to base 10 or whatever, but actually you're not doing any conversion to base 10 whatsoever. Okay, so with that out of mind, the way, what do we do? So generally you have in base B, let's say, let's just make things simple, with 4 digits, base B. What does that mean? We know that that means is powers of b's multiplied by the digits, right? This is a pretty standard thing. In the, that's the value that it represents. So how do we compute this? Well, you could write a loop that computes this, and then the question is, do you write this loop to scan your digits this way from left to right, or do you do it from right to left? Many people, especially beginners, would do it from right to left because They just keep on increasing the power of b's and then multiply by digits, and that's it. But actually, it's easier to do it left to right. And the way that you do it is you set the value that you want to be 0 at the beginning before you do anything. So if you don't read anything, if there are no digits, then the value is 0. Then what your loop is going to look like is that you're going to take the number, you multiply by the base plus the next digit. I should say the value of the next digit. Okay, so what does that mean? So at the beginning, you get 0, and then the first digit, you get the value of A3, and then it was 0, so 0 times b plus that. Okay, so take the previous value, multiply by b, and add that at the next digit. Now the next digit, I'm going to take this and multiply by b and add the value of the next one. And I do that again, multiply by b and add the next one. Notice that this A3 now accumulated 2 powers of b's. If you expand it all out, A2 will accumulate 1 power of b, A1 will have no powers of b, and then you do it again, and then A1 will have 1b, A2 would have the 2 powers of b, and A3 would have the 3 powers of b. And if you do it this way, you don't need an extra variable to keep track of powers of b's. There's something that's similar for evaluating polynomials. So for example, if you have a polynomial like p of x, it's equals to this, and you ask what is p of 2, well, that's really the same kind of calculation. So you can read it from left to right, and instead of multiplying by p, you multiply by value of x. And this is sometimes called the Horner's rule. So if you want, you can look that up. And so this is basically what you do. In this problem, the only thing that's a little bit different is, first, what is the base? The base is the length of the string in the source language. What is the next digit value? Well, you have to look it up inside the string, and the position of that character in the string would tell you the value, right? So, for example, here, what is C? If you do a string search on the character C, it will return index 2, and that's exactly the value of C in this system. Okay, so then what about converting from integer to base b? Well, the idea is that the last digit, it's simply the value mod b, and then you do divide everything by b. So you grab this a0, and then when you divide by b, all of these powers drop down by 1, and now you basically have the same problem. So if you mod b again, you'll get the next digit and so on. So basically all you do is you write a loop. Okay, so you write some kind of a loop where you repeatedly say next digit, well, I should say, okay, let me say last digit is num mod b, and then num divide by b, and when do you stop? If num is greater than 0, you keep going. If it's 0, you're done. Now, these digits will come out backwards. So you get the last digit first and so on. So if you're collecting them, you need to make sure that you print them out the correct order. Okay, so you will get the digits backwards. Also, in this case, in this problem, you don't have to worry about it. But if the number 0 is a possibility, then this loop will never enter, and you'll get no digit whatsoever. And so that's a special case that you have to worry about if you want 0 to be printed as 0, right? Because otherwise this would not generate anything. Okay, so that's basically the idea. And of course, yeah, this is the digit. So this might have I should say the value of the last digit. So if the value is 3, then you have to go and look up 3. What is 3? 0, 0, 1, 2, 3. So you have to look up the target string and index, use the value of that digit to index into this string. And that's pretty much it. So let me show you my code. Oops. It's basically what I told you. Okay, so there's the main program, which does this, just read a number of cases and then call my main routine that many times. And then my main routine, my main solving routine, I read in the number that you're given. I read it as a string, right? So don't read it as a number because the number could be a string of digits in the source language. It might not be standard digits. I read in the source string for the source base and the target. Then I figure out the base, whether it's base 2, base 3, or base whatever, simply as the length of these strings. Then I convert to the numbers, right? So this is basically what I told you. Start with number 0 for each character in the original string, multiply that by the base, add the value of that character. And I use string find to figure out what is the value of that character. Then I build up the string of the output. So while the number is bigger than 0, I take the num mod the target base that will give me the value, and I look up in the string to figure out the actual character I should use for the digit, add it to the string, and then I divide by the new base. And I do that until numbers not greater than 0 anymore. And then I realize, of course, that the digits are added in the wrong order, so I reversed it before I print it up. Okay, so this is again a reverse is an STL function that allows you to easily reverse the elements in a container, right? So I don't want to say that this is trivial, but these are things that I would say are fairly standard things that you learn in, I don't know, your first year computer science, how to convert um, these numbers from one base to another, and then you just have to code it up with this extra funny business of the digits being a little bit different from the usual ones. Okay, so what should I do? Which one should I talk about next? Actually, maybe I'll talk about these other ones first. Okay, jumbo communication. So basically, you have these values that are sent scrambled. Okay, so you have up to 10 to the 5 or 100,000 different values that are sent corrupted or encrypted, and you need to unencrypt it. And what is the encryption? It will be whatever number you get, you shift it to the left 1 bit. And then if you read this thing on the bottom, uh, if you shift it by j bits, the bits of x are moved j steps to the left, the j most significant bits are discarded, and zeros are added as significant bits of the result. And then you do a bitwise exclusive OR. So for example, they say that if you take this number as x, 1011000, and you do a left shift, wait, no, that is not the example. This is just showing you what an exclusive OR and what the left shift is. It doesn't actually show you what happens to this exact operation. Okay, so let's take a look. Okay, so everything is 8 bits. Okay, so I don't know. So this is 8 bits. So this is x. Then x left shift 1 would be like this. So everything moves 1 over. Okay, and then you do exclusive OR. So what is exclusive OR? You look down the columns. If they're both the same, then it's 0. If they're different, it's a 1. So it's 1, 1, 0, 1, 0, 1, 0, 1. And the idea is that you get this, you want to recover the original. Now there are lots of different ways you can do this, I guess. One way you can do this is to realize that this very first bit that gets shifted in on the right, when you do a left shift, is always 0. So that means that this bit in the output, it's always the same as this. Okay, so you can figure out that this bit of X and the output of this X exclusive or X, the least significant bit, it's always the same. Now that you know where this bit is, you can then move over to here, and then you can recover this bit by taking the next bit exclusive OR with this. One exclusive OR with 1 is 0. Then you can do this. You can move it over here, 0 exclusive OR is 0. You move it over here, 1 exclusive, and you can do this one bit at a time from the right to the left and get everything by picking it off one bit at a time. Okay. But more importantly, I guess, is that if you know what is the output, what is this scrambled output, X is uniquely determined. Okay, there's no if or but. And maybe it's a little bit harder to see. There is no way that you can have two different X's that gives you the same scrambled output. Okay, so basically this is a one-to-one function, so it's uniquely invertible. Okay, maybe you don't care about that because the problem, the way that they ask you in the problem kind of implies that if they give you a scrambled value that you can never have two different answers, right? In no place did they tell you that that there are two possible answers that you can then scramble to. So because they didn't tell you that, you can perhaps assume that it is unique. But why didn't they bother telling you? Because you can, if you want, you can actually figure it out and realize that there is no two different input that can give you the same output. Okay, so you can write this. But what I want you to do is to think about a different way. Okay, what is a different way? If I have X, I can very easily figure the scrambled. So this is the input, and this is the output. You give me an X, I can compute the output quite easily because I pretty much know what is the expression, right? There's no mystery here. They even give you the formula. All right, so now what? Well, why don't we just loop through? I know that they just care about 8-bit quantities. So let's just loop through 0 to 255 and apply the function, whatever f is. I write a function f that does this stuff. And then it will give me the scramble. And I know it's unique. So I don't know, maybe 0, well, 0, I guess it's just 0, and 1 would be something else, and so on. 1 might be, so what's 1? 1 is like 3, I think, and so on. Why don't I just use this and build a new table that is the inverse of f? Okay, so what do I mean by that? If I see 0 goes to 0, well, just put 0. If I see 1 goes to 3, I would go to the entry index 3 and put 1 here. Okay, by computing f of 1 equals to 3, I can then go back and come here and say f of 3 is 1. And I would just fill in this. So 2 is, what is 2? 2 is like this. And then left shift is this. So 2 is like 6. So then 6 would be 2, for example. And I just build this table. And now, whatever output you tell me, I just come here, look up the table, and that's it. And this is a lot easier to code than doing this kind of figuring things out one bit at a time. I mean, it's correct. Whatever that approach was correct. And but this is a lot easier to code. So what I want to say is that sometimes you can look at a problem and instead of doing things the, I don't know if you want to call it the smart way, try to figure things out like that, maybe you realize there are actually not that many possible things that they can ask you, and there are really not that many possible answers. So let's just try them all. And in this case, we're basically trying them all by saying, let's compute the answers for all possible output, figure what the input is. I used the word input and output. I'm now swapping them because the input of the problem is actually output, and the output of the problem is actually original input. So I compute all possible messages and see how they scrambled to build a table that allows me to just look things up. And more importantly, it is really easy to build this table. I don't have to do anything by taking things apart because um, they actually told me the formula, right? So that's basically it. The only thing that you have to be a bit concerned about, okay, so there's one thing that you have to be a bit concerned about. If x is this, and you shift left shift, you will get this. If your data type is more than 8 bits, so if you use a normal integer, which is 32 bits, you will end up with something like this. And then you will end up with something like this, which means that this will be bigger than 255. And if you try to use this, you're in trouble. So what's the plan? Well, just get rid of anything that's bigger than 8 bits. There are different ways you can do this. And one way you can do this is, for example, just to use an 8-bit integer, okay? Or you can just take the 32-bit integer and then do a bitwise AND with this value, which is just 8 ones. Right? So this is groups of 4 to F. So if you do 0xFF and do a bitwise AND, anything that is outside of the last 8 bits will be wiped out. Or you can decide to use an integer for 8 bits. So what's an integer for 8 bits? A character is guaranteed to be 8 bits, but you have to be very careful when you do bit operations with any integer data types that may involve the most significant bits. And what I mean by that, if you have taken some hardware courses and know how numbers are represented, you may have some differences between what it's called arithmetic shift and logical shift, and which one is which. If you have a 1 bit in the most significant bit for a signed integer, that means it's a negative number, and things can be a little bit funny if you try to do shift. So the rule of thumb is use unsigned if you can. Okay, that will make sure that you're not doing anything strange, and then have numbers treated as negative numbers. Okay, so I just want to show you my code. What was it called again? Communication. So here it is. So here's my encode function. The only thing that I changed was to do the get rid of anything that's more than the last 8 bits. But otherwise, it's what they tell me. I have a function that basically just compute the encoding of every single possible value from 0 to 255 and assign the entry for this inverse table lookup. And then once I call init, I read n, and then I just basically read in every input, and then output the table lookup value. There's a little bit of I don't know, a little bit of mess, I guess, to decide whether you want to print a space or not to separate entries. But other than that, the actual computation is fairly straightforward. Of course, what I said at the beginning, where you pick things off one bit at a time, will work, but it is a lot more involved when you write it, and perhaps more plausible chance to mess up. Okay, so this is not a problem where I would say, algorithmically it's very challenging, but I want to show you sort of a different mindset on how to write the solution for this that will be a little bit easier to write. So again, what is the takeaway? If you can see that there's a limited number of inputs and outputs, then instead of reversing this by some sort of mathematical computation, just compute the forward process and then remember all the possible output and then use the reverse table to look it up. Sometimes that's a lot easier than actually trying to invert a mathematical function. Okay. All right, what's next? Towering problem. Okay. So you're given these boxes, 6 of them. Okay, so there are 8 positive integers. The first 6 represent the height of the 6 boxes. You're supposed to stack them into 2 towers of 3 boxes each. These boxes have to be from biggest to smallest. And then you're also told that the towers, the total height of these towers will be some specified numbers. Everything will be less than 100, and the box heights will equal the sum of the tower heights. So it's actually possible to do. No 2 boxes will have the same height. I'll put the heights of the 3 boxes in the first tower, then the heights of the 3 boxes in the second tower. Each set of boxes should be output in order of decreasing height. And then here it says each test case will have a unique answer. So there's always an answer, and there's never more than one. Okay, so you don't have to worry about that case, what to do if there are multiple answers or what to do if there are no answers. But it's not too difficult to try to avoid that. Just deal with that if the question asked was something different. Okay, anyhow. So basically, you have 6 boxes. You have to put them into these 2 towers. Again, I don't think that this is a hard problem per se. There are many ways you can do this. But the question is, what is the fastest way you can do this correctly when you write the code, right? You don't want to, if you have some convoluted logic on how you stack these things together and which one you try first and so on, right? Then it's a little bit of work. I mean, you might say, okay, the biggest one have to be the biggest one in one of the 2 towers. The smallest one have to be the smallest one in one of the 2 towers. And you try to do all these things to try to optimize. Maybe you can do that, but the more things you try to add, the more stuff you have to write. We are trying to figure out how to write this as easily as possible to get the job done. All right, so you have 2 towers. I just call it 1, 2, and 3. Or I should use 0 base indices. You know the height 1 and height 2 of these towers, right? So immediately you realize that there's 6 positions you want to put stuff in, and you have 6 heights. So well, let's call it capital H1 and capital H2, and then H0, H1 up to H5 are the heights of the different boxes you're given. And basically, what you're looking for is just a permutation of these things. Assigning these boxes to these 6 positions is just a permutation of these heights into boxes. That's it. And because there are only 6 of them, there are only 720 different possibilities. So you might as well just try all permutations. Some of them won't make any sense, but we don't care. Why don't we care? Because the code that you have to write to eliminate those things are probably more not worthwhile than just trying all permutations. So what are we looking for, right? We're looking for a permutation of 6. So H, I don't know, could be like this. Who knows? Where this first part add up to H1, this second part adds up to H2. Within these 3, they are sorted in decreasing order, and within these 3, they're sorted in decreasing order. So you want to be able to just try all permutations, in this case only 720 of them, and check that these 4 things are true. If you can, if these things are true, you're done. And you are told that there's a guarantee that there's exactly one permutation that works. So all we have to do is check all these things. And the question is, how do we do it as quickly as we can? And here, if you know the STL, pretty much everything that we want to do, it's part of the STL. So first, there's something called mixed permutation. What does it do? You first put an array of all the items sorted in increasing order. So make the smallest first, make the largest last, and so on, sorted. And then if you keep calling mixed permutation, it will step through all possible n factorial permutations in lexicographical order. So for example, if it's like 1, 2, and 3, you sort it. Then the next one would be 1, 3, 2. Then it'll be 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. And then when you call next permutation on this one again, it will return false. So the next permutation will return true if there is a next permutation, and will scramble things for you to get to the next permutation. Otherwise, it will return false and tell you that's it. That's the end. Okay, so next permutation, it's a function that allows you to easily step through all the permutations. Now, for bigger problems, if it's not 6 factorial, but maybe even 10 factorial is fine, because 10 factorial is only about 3 million, 3.6 million, and 11 it's about 30 some million. So even 11 factorial is fine, but bigger than that, you do not want to step through all the permutations. You probably need to do something else to prune things as soon as you know something is not going to work. So for example, if you're trying all the permutations, you realize the first 2 numbers are out of order, there's no point trying all these other permutations. Right? You can prune things. However, because the numbers here are so small, I'm not going to write extra code to bother with that. It's just not worth it. Okay, so since it's not worth it, we'll just try all permutations. All right, how do we know if a certain range add up to the correct thing? There's a function called accumulate, which has the beginning of the range, the end of a range, and then a number that you use to initialize the accumulator. So when you're adding a bunch of stuff in an array, for example, you usually initialize a variable to be 0, and then you accumulate all of the items as you see them. This is what you initialize it. If you don't want to initialize a 0, you want to initialize it something else, initialize that. And that will give you a range. So you can use accumulate on each of the halves and ask it it comes out to be the right thing. Okay, what about checking that the sequence is sorted? Well, believe it or not, there is a function in STL called isSorted with begin of the range and end of the range. And by default, it will assume that you want to sort things from smallest to largest. And it will turn true if it's sorted or not. But we don't want that, right? We want from largest to smallest. So there are two ways you can do this. You can decide that actually this is, you sort everything backwards. So you sort things um, from smallest to largest, but when you print it, you have to reverse it. Or you can specify an optional third parameter, which tells you what comparison function to use. And in STL, there's something greater, and then which type of greater. So in this case, for integers, and that basically says use the greater than function instead of a less than function, which then effectively reverses the sorting. Okay, so with that in mind, it's just a matter of chaining everything together. So here's my code, fairly short, 31 lines. I have my H1 and H2. I have my array of H heights. I read everything. And if I was going to use next permutation, remember always to sort your permutation so it goes from smallest to largest. Otherwise, it will not step through all possible permutations. And the standard thing to do is to use a do-while loop. So the very first permutation, it's always processed. And then we call at the end of the loop while next permutation. So this would generate the next permutation if there is one. And if there was a last one, it will break out of your loop. Okay, so this is one of the few times where writing a do-while loop is actually the right thing to do. And then what do I do? So this is where my check is. If the first three are sorted in the wrong order, in the backwards order, if the last three are sorted, if the sum of the first three is H1 and the sum of the last three are H2, if all of them are true, print it out and I break. Now, you don't even need to break because you're told that there's only one solution. So you can, even if you found your answer, you can still go through the remaining permutations. But anyway, because it's so easy for me to write the word break, I might as well just do it. And this is it. That's it. Okay, so um, again, I'm not saying that this is, really hard, but I want to show you how to use STL and other kind of functions that are already available to you to advantage to basically make your life a lot easier, right? It's not just that you write less code, but using these functions makes it much easier for you to get it right. Yeah, imagine you have to write your own code to make sure that the first three are sorted and last three are sorted. It's not that you can't do it, but you have to write more code, and writing more code means that there's a greater chance to mess up. But when you use the word is sorted, right, that's very descriptive of what you're doing. And then, it makes things a lot less confusing, even if you have to debug. Okay, so in this case, what I want to show you, what I guess take away is, first of all, to realize that this is actually a permutation kind of fun problem. You're looking for all possible ways to permute. Now, you might not think of this as permutation originally. You might think of it as, you might think of it as assigning heights to different positions. But whenever you have these things called an assignment problem, where you assign things into positions or into jobs or whatever it is, where everything has to go somewhere and no two things can go to the same place, then that's essentially a permutation. All right. Okay, next one, fruit basket. Okay, so you want you have up to n fruits, up to 40 fruits, and they have some weights available. The weights are in grams. Each fruit can be put into the fruit basket or not, and so there are 2 to the n minus 1 different baskets. Of course, you ignore the empty set. So if you have n things, the total number of non-empty subsets is 2 to the n minus 1. Basically, each item can be part of the subset or not, right? And of course, you do minus 1 because you don't want the one that is empty. You want to know, out of all the fruit baskets or subsets that are at least 200 grams in total, at least, what is the total weight of every one of them? You're also told that every fruit will have weight at least 50. Okay, so this is actually important. Why is it important? Because you will not have any, how do I put it? If you look at 4 pieces of fruit, then you know for sure, absolutely sure, that it's already past the 200 grams limit. And so you should count it. So any subset of size at least 4, you want to keep it. You want to keep it. Okay, so what should we do? Right? Because all the subsets of size 4 or more must be counted. So maybe you say, okay, let's just look at all possible subsets of size 3 or less and see which ones I need to count. And so basically you do 40 choose 1, all the subsets of size 1, 40 choose 2, 40 choose 3. If you want, you can even write a single, double, triple loop or whatever, and so on. But there's some danger to that, because if you write hard code in a double loop to try all possible pairs of fruits, what if n is not 1? What if n is 1 and you don't actually have any pairs to talk about, right? Because that's possible. So if you're hard coded looking for all pairs or all triples, you could run into trouble later because there might be no pairs or low triples to look at, and then it could be a bit of a pain to rule those out. But also, you also have to figure out the total weight of all the fruits in the baskets. So even if, let's say, all the fruits are at least 200 grams, that means all possible subsets, non-empty subsets, are eligible. How do you figure out the total weight of all the fruit in the baskets, in all possible baskets? Right? It's you have to think about this, how to actually compute that, because you don't want to actually go through 2 to the 40 minus 1 different baskets to sum it up. That's going to be impossible. So the first thing to realize, I guess, first thing to think about is, what if every fruit is at least 200? So every possible subset I need to count, right? So maybe I have A0, A1, these are the weights of the fruit, up to AN minus 1. I need to look at all possible subsets. Now, how do we generate all possible subsets? Typically, what you do is you say, well, A0, you either choose it or you don't choose it. So you don't choose it, or you choose it. And then you split into 2 cases recursively, and then you decide whether you choose A1 or not choose A1, and then choose A2, not choose A2, and so on. Right? This is a standard way of trying all possible 2 to the n minus 2 to the n subsets, and one of them will be don't choose anything, and that branch you forget about. Okay, now, if you choose A0, then of course the weight of A0 would be part of all the subsets on this branch. And if you don't choose it, then of course A0 is not part of this, so you can, if you only want to know how many times A0 appear in a subset, because you want to know what is the total weight that A0 contributes to in all the subsets, well, none of this matters because you don't choose it. And here, A0 appears once in every subset over here. Well, how many subsets are there? 2 to the n minus 1, right? Because you chose A0, now you have n minus 1 things to worry about. How many subsets are there? 2 to the n minus 1. A0 appears in every single one of them. So A0 contributes to the total weight exactly this much. Okay? So that helps you a lot, right? Because you can make the same argument with A0, A1, A2, and so on. And so it turns out that in a case where everybody is at least 200, the answer is just this. Everybody contributed exactly that many times. Okay, that's the total weight. All right, so that's observation number 1. The second problem, of course, is what if not everybody has weight at least 200, right? So some subsets will not work, so you have to worry about that. And here's what we're going to do. So A0, A1, A2, it doesn't actually matter whether you decide to choose A0 first or choose AN minus 1 first and work your way backwards. None of that really matters because they're all symmetric. So let's just choose the last one to make things a little bit easier. So why did I say it's a little bit easier? Because if you're passing an array of weights, you pick up the last one, then you can just pretend that the array is one element smaller. Whereas if you do it the other way, strip off the first entry, then you have to readjust the indices of where you start as well as how many there are. Okay, but anyhow, let's say we decide to do this one. So let's just make things concrete. Let's say this is 20. Well, if you decide to choose it, or don't choose it, that means that I still have to make 180 if I choose it, because I wanted to make 200 to begin with, right? But now that I take 20, I still need to make 180. Whereas if I don't choose it, I still need to take 200. Okay, and maybe the next one is 60. Well, let's just make it 200, right? So if I choose don't, right then now, by choosing both these two, this is now, well, let's just say minus 20. Minus 20 doesn't really make sense, but minus 20 just means that I'm already done. I don't need to worry about whether I have the minimum. And once I have that, now I am in the same case as I had before, where I just say, well, any possible subset of these things are okay, so I use whatever calculation I made before, and now I can figure out the total weight of contributed by A0 to AN minus 3 in this chunk. But what about AN minus 2? Well, I need to know how many times AN minus 2 contributes in this branch. The only way I know, it's not just that I need the total sum, the total sum of things. I also need to know how many subsets there are that works, because the number of subsets that works multiplied by AN minus 2 is the answer. that an minus 2 contributes to. And similarly, if I want to know how much an minus 1 contributes to in this whole thing, I need to know how many subsets there are and multiply by that. And so what that means is that not only do I need recursively to know what is the total sum of all the eligible subsets, I also need to know how many subsets there are. And this is basically the idea. Now, you might say, well, if I just do this recursively and every time I split off two ways, isn't that just 2 to the n, which is what I'm trying to avoid? And the answer is sort of yes, except that because AI are always at least 50, I know that none of the branches on the right can be more than 4 steps. Because as soon as I hit 4 of these, I'm guaranteed to be at least 200, and therefore I can just stop the search. And that's how this allows me to actually make the case that this is fast enough. Otherwise, if I don't have this guarantee, I might really have to do 2 to the n. And that's no. That's way too slow. I think that's about it, I guess. You could say, well, when you recurse, right? So when you recurse, actually, you're always going to have how many you have and also how much more you need to make, or more if you want. And then, yeah, how much more you need to make. At the beginning is 200, and minus 20, you can just pretend to be 0. So there are actually not that many different input you can have because there are only up to roughly 200 different numbers on what you still need to make, and also how many things you still have to look at. So you can, in fact, actually use dynamic programming if you wish. And we will talk about dynamic programming later, but in this problem, it's not required because we have a hard limit of how many times you can actually choose something, as long as you prune. Okay, so as long as you do this pruning. If you don't do this pruning, that's not good enough, but maybe you can use dynamic programming then. Okay, so uh, what was the problem called? Fruit basket. Okay, so let me show you my. Okay, so I use 64-bit integers. Why? Because n is 40. Things are 2 to the 40 in terms of subsets and numbers and so on, right? So 32-bit is definitely not enough because 32-bit integers allows you to go up to 2 to the 32 or 2 to the 31 if it's signed. So I need to use 64-bit integers. So I have a pair, and the pair represents two things. First component is a number of subsets that I have found that works, and the second number is the total weight of these sets. Okay, and then my 3 parameters. Well, first parameter is just the weight of all the objects, and it's the number of items, how many of the first n items I want to use, I want to look at, and min w is basically what is the minimum weight that I still have to accomplish. And at the beginning, I read the input and I just say, pass you the whole weight array, all of them and or n of them, and I still have to make 200. And then the total weight is the second component. Okay. Okay. So what if the minimum weight I still have to make is 0 or less? That means I don't really care anymore. I have already made everything, the minimum weight, so I just take every single possible subset. And I'm going to actually also include the empty set, okay, because the empty set It's needed when I put it back to the parent that calls me to add their item into the empty set to make it non-empty. And it's okay if you include the empty set, because at the end of the day, I'm asking for the total weight. So the empty set total weight is 0 anyway, so it's not going to change the actual answer. So here it is. So this is 2 to the n. Now I have to be a bit, so 2 to the n, when you want to compute 1 to the, or 2 to the any number, you can use the number 1 and do a left shift n steps, and that will be 2 to the n. That's equivalent to 2 to the n, because the number in binary 10000 and so on is just a power of 2. But I have to be careful, because 1, if I just write 1, it will be a 32-bit integer quantity of 1. So if I shift it 40 steps, it will actually overflow. And by putting ULL as a suffix, it forces G++ to treat the 1 as a 64-bit unsigned integer. So unsigned long, that's what that means. Okay, anyhow, that's the total number. Exactly half of them, so 2 to the n minus 1. So I could have, instead of using num over 2, I could have shifted n minus 1 step like I did. And this just basically add up all the weights, multiply by 2 to the n minus 1, like I said before. And then the total weight of all the subsets is this, and the number is 2 to the n. Okay, so that's one base case. If I already have the minimum required. The second one, what if I have nothing left? I have considered all the things, all the items. Well, then there's no set that will work, and the total is 0. Okay, so why do I say there are no sets that will work? Because I have already taken care of the case where I have satisfied all the weight requirements, the minimum weight. So if I got to here, I have not satisfied my weight requirements, and I have no more things I can add. So therefore it doesn't work. And then here, now that I'm not in my base cases, then I basically do this. Either we choose that object or not. If we don't choose it, then I don't do anything. I just recurse with one field item. Otherwise, the second one is I choose it, and now my minimum weight that I need to make is reduced by that last item. And in that case, I will also add to this total that item times the number of subsets that came back. And then my answers are just the sum of these two. So I add up the number on both cases for both the numbers and the total. And that's it. Again, as I said, if you want, you can use dynamic programming here as well, because the total number for n is at most 40, and this is between 0 and 200. So really, the total number of things you can ask is it's basically 20 times, 200 times 40, which is not that big. But since we haven't gone to dynamic programming yet, and this is good enough as is, I'll just leave it like that. Okay. The last one is a little bit involved, perhaps. So you have a bunch of numbers, 1 to n. They are happening exactly once. So basically, you have a permutation. You have this algorithm called turbo sort that basically alternately move the smallest element to the first position, then move the biggest element to the last position, then the second smallest and the second largest, and so on. Now, it may be that at some point, the smallest number, for example, might already be in the first position, and then you'd have to swap, or maybe it's very far away and you have to swap. And the question is, how many swaps did you actually do? When you try to move things from one position to the next, you can only swap adjacent element. consecutive elements. So it might take many steps to swap, right? So if you have position, so let's say where it's zero based, if you have something at position 2, you want to get it to position 1, you have to do a position, you want to go from position 2 to position 0, you need to swap it to 1 and then to 0. So it's 2 swaps. And if you haven't heard of this before, this is basically kind of like double bubble sort, except that instead of always finding the min and swapping to the bottom, you kind of alternate between min and max. And there's a name for this. Some people actually call it the shaker sort algorithm, cocktail shaker, because you're like shaking on one end and then shake it to the other end and so on. Anyway, you don't want to actually simulate this in counts because this algorithm turns out to be n squared time and n is 100,000. What we want to do is to try to find out a way to do it better. All right. So let's look at an example. Actually, they have some example. Uh, let's do this one. 5437126. 5437126. Okay. And the positions are 0, 1, 2, 3. So I know that the problem statement use one base position, but I'm just going to use 0 base. And actually, um, just to make things, okay, I know that I don't know if that's make things simpler, but um, I'm going to use 0 base numbers as well. Okay, so I haven't really changed the problem. I just make everything 0 based. Okay, so I want to move 0 to the 0 position. I want to move 6 to the 6 position, and so on. Now, the first step is I'm going to move this 0 to here, right? So after I move this, first of all, how many steps do I need? Well, 4 steps, right? Because I'm set position 0, I'm with 4 steps, so I need to move 4 steps. And now, because I am swapping the adjacent ones, everything stays the same relative to each other. So 4, 3, and 2, 6, they stay in the same order. I don't change their order. Now, the largest one has to go. So the largest one has to go this way, 2 steps. And maybe I'll just kind of put a box around it so that we know that these are done. Then 1 has to go this way in 3 steps. How do I know it's 3 steps? Because it's position 4 to position 1. So that's 3 steps. And now these 2 are fixed. The middle are like this. And the next step, nothing happens because 5 is already there, and so on. What I need to do is to keep track of what? I need to keep track of, for each element, what is the current ranking in the remainder, right? So at the beginning, I know that 0, right? 0 is here. And somehow I need to know that I'm at position 4. Okay. But then when I remove this, when I move it out of the way, then essentially I can just pretend that I got rid of it, right? And now I need to know that I've relabeled these things. Instead of 4, 5, and 6, this becomes 4 and 5. Why be 4 and 5? Because if later on I want to move a 1 to here, I know that the next step is to move things the other way. But if I were to move things to a 1 this way, I know that that's just 4 steps. Okay, but now I'm going to move the 6 this way, right? I know that I need to move 2 steps. Why? Because the last one, the last element, the position is now 5. I know that the current ranking is 5. And then I move it over here, basically effectively getting rid of it in my consideration. And now I need to know that my indices are updated to 3, 4 like this. Okay, so at any time, basically what I'm doing is I have an original position of these numbers. It's for position of 4 is 0, position of 3 is 1, and so on. But as I move things out of the way to the correct spot, anything that comes after will now have the official position shifted, right? And that's the problem of how do you keep track of these positions? Because when I do this, when I get rid of this, I have to update everything, all the position that comes after by one, subtracting 1. And if I were to do that by touching every one of them, that's going to be a really big problem. It's going to take a long time. So instead, what am I going to do? So forget about the actual numbers in this array. If I want to know what is the position of everybody, like what is the position of the thing in here, for example? Well, one of the things I could do is to initialize an array that has only ones, at least conceptually. We won't worry about actually storing this array. Okay, so they're all ones. So this is my, let's call it present. Is it even, this array basically says, is the element in this position still under consideration? Yes or no? At the beginning, all of them are still under consideration, but at some point, once you decide to swap them out, then they become 0. And then we can have a prefix sum. What is a prefix sum? A prefix sum at each position, it's simply the sum of everything from the beginning of the array to the next one. So everything from the beginning of the array to this point, okay, so we are not 0 base anymore, but this number basically tells you where everything is. Right? You just have to adjust with the 0 base versus 1 base. Now, if you were to swap this one out to the right place, so this becomes 0, you don't care about anymore, then all of a sudden, all of these cumulative sums would go down by 1, right? And of course, you now have 2 entries that have the same cumulative sum, but because you know it's not present, so you know that this is kind of useless anyway. And now these numbers are automatically updated if you have a way to compute these prefix sum or update these prefix sums quickly. And this is a data structure called a Fenwick tree or binary index tree. It is exactly the right data structure for that. And I have a separate video that explains how this works. But basically what happened is if you have an array, an underlying array, you don't actually even need this underlying array. But if you have an underlying array, the Fenwick tree data structure will allow you to ask for the cumulative sum at any point in this array, and also allow you to update an entry in the underlying array and have all the prefix sums updated in log n time, right? So if you, for example, if you just do the naive implementation and just say, okay, set this to 0, so now I have to go scan through everything afterwards and reduce it by 1. That's not log n time. That can be linear time if you're trying to remove something at the beginning of the array. So you can go, if you want to know how that works, you can go and read that, watch that video. If not, then you can just use this. Okay, so let's see how my code works. Okay, so first I went to my code library and then it just pasted the Fenwick tree code. So you can go and look it up if you want. Okay, so this is the actual program after that library. Okay, so what do I do? First, I read in N. I have the two arrays. A is the array that of the original values. I'll tell you the position, what that means later. I will create a Fenwick tree that has n objects to keeping track of n, an array of n and its cumulative sum. For each one, I read in the value n out of the element. Position remembers where it is. So what does that mean? If I have, okay, so again, I'm converting everything to be 0 base. So this is my array of 6 things, let's say. And then my elements are 2, 4, 1, 5, 3, 0, let's say. Then my position would just say position of 0 is at 5. Position of 1 is at 2. Position at 2 is at 0, and so on. Okay, so I know where in my array, position of 5 is 3, sorry. If somebody tells me I need to move 3 now, where is it? Well, I know it's at position 4. Okay, why do I need to do that? Because now I'm going to use this underlying array like I had before, which has 1, 1, 1, 1, 1, 1 to indicate that all of them are present. And now, if you want to remove 0, I'd go in here and I say, oh, I need to move this one. And now you realize that the cumulative sum is 5, or 6, sorry, and the cumulative sum of this position is 1, so the difference is 5 steps. And then you can say, okay, let's update this present array to remove that and then update all the cumulative sum. So by having a position array, I know quickly where to look in my original array, which position I'm trying to move. And then here, Fenwick tree. So at the beginning, when I initialize this, I pretend that the underlying array that I'm taking the cumulative sums of, it's all zeros. So here I just say increment the entry of the underlying array at I is positioned by 1. And that will make it, that will make the underlying array of the cumulative sum all ones after this loop, right? Just like that. And then here, for each of the passes I need to move stuff, first, so for each of the steps I ask, well, is it an even step or is it an odd step? Because even step means that I have to move it to the beginning, and odd step means I have to move it to the end. And this basically figures out, is it the next smallest number to move or the next largest number to move, right? First is the smallest, and then the largest, and then second smallest, second largest, and so on. So this is a bit of arithmetic that you have to figure out. And then if you're moving the smallest one to the beginning, then I just look at the cumulative sum of that element. So look at the element, look at its position, figure the cumulative sum minus 1. That's because I have So one base cumulative sum, and that will tell me how far I have to move to the left, the smallest element to the left. And similarly, if I want to figure out how far I have to move to the right, I ask again the cumulative sum, but then the cumulative sum on the right endpoint is n minus I because I have removed that many steps from the previous steps. And then that will tell me how many position I have to move. And in either case, after I move them, figure out how many things I have to move, then I take the underlying array, the present array that even though it's not explicitly stored anywhere, and I change that entry by -1. So I take whatever it used to be, which is 1, and I increment the entry by -1, which means that I am making it 0. And then all the prefix sums would get updated, right? So I want to introduce this data structure to you that allows you to keep track of cumulative sums dynamically as you increase or decrease entries. And one of the applications is to keep track of the ordering of things, of a set of stuff that may be added and removed at runtime. Okay, so that is all I have to say for this week. Turbo is for sure something that's much harder, but at the same time, if you have the Fenwick tree code and just use it, well, you still have to figure that out, but it's not as bad. You have there's a lot of code in the Fenwick tree stuff, but you don't have to write it yourself. Okay, anyway, I guess I'll stop here, and maybe I'll make some other videos about data structures again next time.